Okay, so now we're going to look at another method for integration. So far, all we've had is power rule, or we know how to integrate sine or cosine. Keep in mind, there's many functions that we cannot integrate. We're just showing you the ones that you can. So here's another method to integrate, like if it's not just a straight power rule or something like that. It'll look to you like it's a product rule or something, but it's not a product rule. It's really a composite function. So it's the reverse chain rule. Remember, the derivative of a composite function, we use chain rule, where you're talking about the derivative of the inner. So we're looking at reversing that idea. We're looking specifically at functions where we could tell like chain rule was applied to it, and now we want to go backwards and integrate it. So you're almost looking at, like, the way I think about it is you're looking at integrating the result from chain rule. And the easiest way to kind of see it, when you see an integral that has the derivative of the inner is part of the integral. If you have a times the derivative of the inner, that's going to be like, that's going to let us know that we can do the integral. We can find the antiderivative of this function. First, we're going to do some derivatives of chain rule to remember what that kind of looks like, and then look at how we integrate those, like just going backwards, and how we can recognize them. Keep in mind that integration is far more picky than differentiation. We cannot integrate a whole bunch of functions, okay? But we're trying to come up with techniques for different types of functions. So this is a very specific type of pattern you're looking for in an integral that allows you to do this method. And of course, it's going to seem like, yeah, no problem, they come up all the time, but that's because we're in this section, okay? In reality, these aren't all over the place. We have to kind of watch out for them. All right, so let's look at this. They're asking us first to find f prime of x for each one of these, right? So f prime of x, well, this is a composite function, right? I could say f of x could be written as h of g of x, like one function inside the other, right? And so h would be our outer function, which would be sine of 3x. And g of x would be our inner function, which would be 3x. So you can see that if I plugged g into h, whoops, this should just be sine of x. If I plugged g into h, I would get f. So f can be defined as the composite function, the composition of h and g. So just a reminder of where that comes from. So the derivative, we know, is going to be the derivative of the outer function, recopy the inner function, times the derivative of the inner function. I just want to remind you of the chain rule. So let's go ahead and do that. The derivative of the outer function sine, so we're going to do the derivative of that is cosine. Recopy the inner function times the derivative of the inner function, which is 3. So f prime of x is going to be equal to 3 times cosine of 3x. So now that's a function that we know how to integrate. So you're going to look out for functions like these. Okay? And what you're really looking for, again, when we do these outside of this section, you're looking for an integral where you can tell that part of it, like this part, you can kind of tell that's one function inside of another. And if you see times the derivative of the inner, so I notice that I'm taking the inner, like I see somewhere else times the derivative of the inner, that's going to be like your license to integrate. Like you're going to say, oh yeah, I can integrate this. This is reverse chain rule, okay? So then we know the integral of this is just going to be sine of 3x plus c. How do I know that? Again, we just did it. That's the only reason I know it, is because we just did the derivative to get back there. Looking at this, I don't expect you to just jump to that. We're going to talk about how we do it if I just start at this point here. The first thing is just recognizing that you can do it. That's what I'm focusing on this page. You can do it because we see this times the derivative of the inner function. That's telling me that, yeah, I can integrate. All right, let's do the derivative of x here. The derivative of an exponential function is itself. So it's going to be e to the cosine of x. Don't know why this is so skippy. F of x equals e to the cosine of x. So that's the derivative times the derivative of the inner, which is negative sine of x. I'm going to pause this and see if I can fix this. Okay, so if we rewrite that in a better format, it's negative sine of x times e to the cosine of x. So now that means, again, that's another integral. They want us to just integrate f prime, which is easy. We know it's just the original f. But if I see the integral of negative sine of x e to the cosine of x, this is another example of how you might see this. You're going to look at it and you're going to say, well, I've got a composite function where the inner function is cosine, right? This is a composite function. The outer function is e. The inner function, I should say e to the x. The inner function is cosine of x. And I notice that it's times the derivative of the inner. This part right here is the key. This is the derivative of the inside function here. So if I notice that, I say, okay, I can integrate this. And I know that it's going to just be e to the, what was it, cosine x, right? Yeah, e to the cosine of x plus c, because this is an indefinite integral. So we have our constant of integration. All right, pause the video, take a second, and do f prime of x here on your own. Practice some chain rule. Okay, welcome back. You've got 16x, 2x squared plus 3 to the third. All right, so now if we integrate that, we know the derivative, the integral of the derivative will just be back to where we were. So we know that that's going to be equal to our original, which was 2x squared plus 3 to the fourth, 2x squared plus 3 to the fourth plus c. Now, here's something to note here, that the inner function is this stuff, and then I see times the derivative. It's not exactly the derivative. The derivative is 4x, not 16x. What matters really is that the x has the same power. That's how we can recognize these if you're talking about polynomials. If it's different by a constant, we can deal with that. Like it's supposed to be 4, but it's a 16, not a problem. It's more about that this was an x to the first and it was an x squared. The powers have to match. That shows me that it's the derivative and it's just multiplied by a constant. We can deal with constants, and we're going to talk about how in a little bit. All right, so one more time, you're going to pause the video and find the derivative of f of x. Okay, welcome back. So you've got x times x squared plus 3 to the negative 1/2. And we could put the negative 1/2 on the bottom. But for now, we're going to look at it like this for the integral's sake. Okay, so again, we notice that we have times the derivative of the inner right here, even though it's not exactly the derivative of the inner, right? Because the derivative of the inner is 2x, but we only have a 1x. It differs by a constant, not a big deal. It's important to note here in our derivatives, when we did chain rule, before we simplified to the 16x, we were getting 4 times 4x times 2x squared plus 3 to the third. This is going to come back a little later, and I'll show you where. And then here, before we simplified it to the 1, it was 1/2 times 2x times x squared plus 3 to the negative 1/2. All right, so this integral will just get us back to our original, which was the square root of x squared plus 3 plus c. So it's more about just the pattern recognition, seeing that when I have the integral, and it looks like I have a composite function. Now, the f prime part is not important for the outer function when you're recognizing the pattern. It's really this g prime. This is easier to see, that the inner function and its derivative are right there. And if they differ by a constant, that's fine. So remember, we know the derivative of that is f prime of g of x times g prime of x. There's our chain rule. And then if we take the derivative of that, the integral of that derivative, we get back to the original f of g of x plus c. So notice once we figure out that that we can integrate, and this is the thing that is our license to integrate. When we see that, the g prime of the inner function there, we know we can integrate. We sort of have to kind of think about now, what would the original function be? So we have to think of what's the integral of the outer function, because that's how we get our f here, remember. The outer function in the integral would have been f prime, so we want to say what was the f whose derivative was f prime, and then we know what our inner function is. We can just kind of copy it. And then we'll talk about how to deal with constants. So we're gonna practice this here. All All right, so we want the integral of this thing here. Now we see that this looks like a composite function, and its inner function is 3x, and we see the derivative of the inner function there, right? So we know that this is of that form f prime of, or I'll do it this way because we put f on the outside there, g prime of x times f prime of g of x, right? That's our integral. So our answer is going to be f of g. It's just going to be the composite function, the original composite function. So remember, this is like this. We have to integrate the cosine. So the integral of cosine is sine, and then we just take the inner function. All right, and we should call that capital F of x. So there's that pattern recognition there. First, we use the 3x and the 3 to see that, oh, this is just a chain rule in reverse. And then we have to integrate the outer function and then just recopy the inner function. So let's take a look at this next one. We notice that the 3 is not on the x. The 3 is on the square root, so it's really the cube root. And then this is just a 2x. We notice the inner function is x squared plus 5. The outer function is the cube root, but the inner function is x squared plus 5. And the derivative of the outer function is right there, 2x, right? So we know that this is a chain rule in reverse. So we think about what's the integral of the outer function, like what's the power rule for integration of x to the 1/3? Well, it's going to be that inner function to the 4/3 times the reciprocal 3/4. And I just recopy the inner. This one's a little tricky to think about. I have another method I can show you in class to do this if you're having a hard time with this, with seeing it. But let's think about this for a second. Once I recognize the pattern that it's times the derivative of the inner function, I have to first think about just integrating the outer function. Okay, and the outer function in this case is x to the 1/3 power, right? It's the part I highlighted in green. That's our outer. And if I integrate the outer, that means I add 1 to the exponent, so now it's x to the 4/3, and I multiply by the reciprocal. And we know that's going to be our integral, except we still have to keep the inner function inside of it because it was a composition. So you integrate the outer and then just replug the inner back in when you recognize this pattern. All right? Okay, so let's move on. So once again, I notice that this looks like a composition of a function where I've got an inner function here, and the derivative of the inner function appears right there. So I'm going to say that if I integrate the outer part, which is sine, I get cosine, and then the inner function has to stay in there because it was a composition or a composite function at first. So we're going to get, oh, wait, what am I doing here? Is this the right one? Yeah, this is the right one. It should be negative, though, because the integral of sine is negative cosine, not cosine. Okay, so again, it just kind of comes down to that pattern recognition here. And I will tell you, once again, that I have another method for you that if you're having trouble seeing this, we'll talk about it in person. Okay, let's try this guy over here. This one's a little tricky as well. So there's some stuff to talk about with this. So which one would be the inner function? Which one would be the outer function? So this one is tough. So usually when you have a denominator, you can try that first to be the inner function. If that's my inside function, then the outer function would have been 1 over x. I just had that plugged into it, right? So I can think of it as, let's write it like this. I'll use a u. 1 over u times u prime. Because I noticed, the thing to notice that gives you that license to integrate again is that 2x plus 2 is the derivative of the denominator. So I can see that this must have been a chain rule. The outer function here is 1 over u. That's the thing to notice. And this one, they like to use this one a lot because it is kind of tricky to see. You got to watch out for this one. When you have a u prime over u, when the derivative of the denominator is when the numerator is the derivative of the denominator, remember that came from ln of u, right? So that the derivative of ln is u prime over u. So if I'm trying to integrate u prime over u, it's ln of u. This is one to just sort of remember. Now, is that exactly the derivative? It is, because the derivative of x squared plus 2x is 2x plus 2. So this one is, it looks tricky at first, but if you can recognize it, it's just the ln of the inner function. Remember, when we're integrating, we got to put absolute value on our natural logs, because our natural logs have to be positive. When the input into our natural log, or the domain of our natural log, has to be positive. So you're looking for this u prime over u. So that's a situation I'd say just watch out for. Technically, the outer function is 1 over x. So the inner function here is x squared plus 2x. And then we see that the numerator happens to be the derivative of the denominator. That tells us this is reverse chain rule. All right, let's look at this guy. All right, so this one, it looks like we have a composite function here with the inner function being 3x plus 2. But now I don't see the derivative. What's the derivative of 3x plus 2? It's just 3. But what we have sitting here is a 1. So they're the same. It's good. This power is x to the first. This power is x to the 0 when there's no x, right? So that's okay. If it just differs by a constant, we said we can deal with that. Instead of a 1, if I had a 3 out there, I would be good to go. Well, you can put any constant you want out there. I could write 3 cosine of 3x plus 2, and now I could differentiate. If I wrote it like this, it would work out, right? So you're allowed to multiply by any constant in there if you just multiply by its reciprocal constant. Because now I didn't change my original integral, right? 1/3 times 3 is just 1, so this 1 just kind of is still there. But then what we can do is we can pull the 1/3 through the integral, and it comes along for the ride, just like derivatives. So constants can be pulled, multiplying by constants can be pulled through the integral. So now I can recognize this as a chain rule. The 1/3 comes along for the ride. And what's the integral of cosine? It's going to be sine. And then the inner function here is 3x plus 2 plus c. All right, so the key here is if it's off by a constant, not a big deal. We can deal with that. We can multiply by the constant we want, and then multiply by the reciprocal constant, which keeps it at 1, and then just pull the reciprocal constant out, leaving the 1 we wanted there behind, so that we can now integrate. That's a trick we'll use often, so I'm sure we're going to see that a bunch here. All right, so here's one where I've got a composite function here. The square root is the outer function. I'll highlight that in green. That's our outer function, our square root function. Our inner function is x squared plus 2. The derivative of our inner function is 2x. So we want a 2x there, not a 3x. So how are we going to deal with that? So if I want a 2x there, I've got a 2x, times the square root of x squared plus 2. This integral will work out nice. This is a reverse chain rule. The problem is, how did I just come up with a 2? How did I change my 3 to a 2? What other number can you multiply by that gives you, that you multiply by 2 that keeps you at 3? So I'm going to say that it's, I'm sorry, not 6/2. So we're looking for a fraction that we multiply by 2 that gives us 3. So that means it's going to be 3 over 2, right? If I multiply 3/2 times 2, I'm back at 3. So the way I look at it is I'm multiplying basically, I want a 2x to remain, like I want a 2 to remain there. So I have to also divide by a 2 to keep it the same. Like that kind of idea. Sorry, wait, no, that's not right. I wanted to do the 3. Sorry about that. Okay. Yeah, no, that's okay. Sorry, I was looking at the wrong example when I was looking at an answer. So I do 3/2 times 2, and that would give me back to my 3. So these, oh boy, I'm having a tough time right now. These are the same number, is how we want to look at it. So you got to kind of figure out what fraction you're multiplying by there. Okay, and what I wanted to do is I wanted to end up with a 2x. So now the 3/2 comes outside of the integral, and I've got a 2x times the square root of x squared plus 2. So now this integral is our reverse chain rule. Keep in mind that the outer function here, I'll trace it in purple, is really x to the 1/2, right? So I've got to integrate x to the 1/2. That's going to be x to the 3/2 times 2/3. Right? So Now we know how to integrate this because there it is right there. That's the integral of our outer. So this whole integral, whoops, I should have the dx included. That whole integral comes out to be 2/3 times the inner function. We have to replug the inner function back in to the 3/2 plus c. And that 3/2 had to come along for the ride. Okay, so it's pattern recognition that this was, we're reversing chain rule of derivatives. Okay, so then the 3/2 times the 2/3, they just become 1. So the answer, the final answer is x squared plus 2 to the 3/2 plus c. Sorry, I was looking at this one a little bit, the coefficient here, which is why I got mixed up. So let's look at this guy. We've got a composition of functions e to the 3x. Our inner function is 3x. The derivative of 3x is 3. So we want a 3 in this integral, but we have a 5. So I'm going to rewrite this integral with a 3. Whoops, I'm going to leave space for my fraction that I want to multiply by. Actually, I don't need to leave space because we know we're going to just pull that fraction out anyway, right? So I want it to be a 3 e to the 3x. What fraction would I multiply on the outside by that would get me back to 5? Well, the 3's have to cancel. Like that 3, I need a 3 on the bottom to cancel it, and I want to replace it with a 5. All right, so it's going to be 5/3 integral 3 e to the 3x. So now I see this as a reverse chain rule derivative. So the outer function is e to the x, right? And the inner function is 3x. So what's the integral of e to the x? It's e to the x, but I got to replug the inner function back in. And then it's times our 5/3 that came along for the ride. This one's pretty easy when it's exponentials because the derivative of e to the x is itself and the integral of e to the x is itself. All right? And by the way, you can check any of these. If you're not sure about them, take the derivative of your answer. You should get back to the integral, whatever you had there. All right, here's another one where you have your denominator is usually your inner function. So in this case, our outer function is 1 over u to the 1/2, right? Because that's a 1/2 power. So there's a couple ways to look at this. When the power of the denominator is 1, I like to just leave it in the denominator because I know that that's u prime over u. I know it's ln. When the power of the denominator is anything other than 1, typically I rewrite it and bring it to the numerator. That just makes life a little easier in terms of recognizing the antiderivative. So that would have been a negative 1/2 when we bring it up top. Okay. Now we notice that the inner function here, right, our outer function, by the way, is x to the negative 1/2. So we're going to do power rule on that. But we notice our inner function is 2x squared plus 3. So when I take the derivative of that, I get 4x. So I'm going to rewrite my integral below. I really want it to be a 4x times this. And now it's a reverse chain rule. So how do I turn my 4 into a 3? What would I have to multiply here to keep it a 3? Well, if there's a 4 in the numerator, I got to have a 4 in the denominator to make those cancel. And then in the numerator, I put what I want to replace it with. I want it to be a 3 there to get back there, right? So the 3/4 comes along for the ride when I integrate. And now this integral is a reverse chain rule. So we want to really integrate x to the negative 1/2 because that's our outer function. So if I add if I add 1 to it, I get x to the 1/2 times the reciprocal, which is 2. So it's going to be times 2. But instead of writing x, I have to include my inner function because it was a chain rule. Actually, I don't need the plus c yet because we're going to simplify a little bit. So our capital F of x is going to be 3/4 times 2 is going to be 3/2. And then we'll call that a square root. 2x squared plus 3 plus c. All right, so that's how we're doing the reverse chain rule, and that's how we deal with a constant. Okay, sometimes we have to do even a little more. If the derivative doesn't exactly match the powers, like when we do the derivative, we're doing the derivative of a polynomial, and I said like all that matters is that the powers match. You can see one here where this is a power of 1, and when I take the derivative, I still have a power of 1. We even have a way around that. when the powers are the same like that. And we can even do it if the power is 1 higher. In this case, we're going to have to make a u substitution. Okay, so you can pause the video here and take a second and read the top part of the video, or the top part of the notes. I'm not going to read to you. All right, so let's look at this one. The inner function is, it says identify the inner function. It's 2x minus 1. What is g prime of x then? Not looking at the integral, just looking at this guy. The derivative of that is 2. And is that g prime, is that 2 part of the integrand somewhere? No, I don't multiply by 2 outside, so no, it's not there. Is that attainable? Like, can I get a 2 there if I multiply by a constant? No, because I've got this x sitting out there. So what the heck do I do about that? How do I get that x in there? We're going to do something called u substitution. All right? So whenever you're going to do a u substitution, because you have this problem of like still an x to the wrong power, again, what I would look at is the power of the inner function is 1, and then this outer function is still 1. They're the same. That would tip you off to a u substitution. So we're going to choose u to be our inner function. That's step 1. All right? Then we're going to find the step 2 is to just use our u and take the derivative of u. So du over dx, we're going to use that notation instead of u prime, is 2. And then we want to solve the equation for dx. So we got du equals 2 times dx. And then I divide by 2. I get 1/2 du equals dx. 1/2 times du. So we don't want to we don't want to write it as du over 2. We've got to separate the constant 1/2 from the du. Okay, so that's step 2 is what we're going to do. Step 3, we're going to write an expression for x in terms of u. So I had that u equals 2x minus 1. What we need to do then is solve for x. So x is going to be equal to u plus 1 over 2. All right? And there's a couple ways to think about that. Sometimes it's good to think of it like this. It's just going to depend on the problem. Other times, distribute that 2 to each one, or put it out front. You could think of it as x equals 1/2 u plus 1/2. You could think of it as x equals 1/2 u plus 1. There's going to be all different ways to think about it. These are all equivalent, and we'll see which ones we're going to use. All right, so we're going to rewrite our integral. So for this case, and we want a polynomial type function. So the integral, the first substitution we make is for x, because we have that x there. We see that x is going to be u plus 1 over 2. Let me rewrite this here so I don't have to keep scrolling up. It's the integral of x, 2x minus 1 cubed. So it's the integral of u plus 1 over 2, I think it was, right? Yeah. Times u to the third times 1/2 times du. So the x, I plugged in this part. The 2x minus 1, I plugged in u, right? So 2 to the third. And then dx, I replaced it with what it's equal to, right? dx is equal to that. That's where I got that from. My u is equal to 2x minus 1, and my x is equal to that. So I used this, this, and this. That's our method. Always going to be the same thing. We're going to choose the inner function to be u. We're going to take the derivative of u and solve for dx. And then this one's called, by the way, separate the variables. This right here is called a differential equation. It's an equation that is already a derivative. We want to get all the variables on one side. So like this means the left side now are all du's and the right side are all dx's. That's called separating the variables. So we get that by multiplying both sides by dx. All right, so now we can simplify this integral so that it can just be a simple power rule. Whereas here it would have been harder to do that. I would have had to do 2x minus 1 to the third. That would be a long polynomial, and then I can distribute the x into that. You could go that route because it's a third. If I make that a tenth, that's not worth it at all. This is the better way to do it. All right, so how are we going to make this thing into a polynomial? Well, again, I kind of like thinking this part as 1/2 times u plus 1 times u to the third times 1/2 times du. It's all multiplication. So these constants, I'm going to jump them to the front and pull them outside the integral. So it's going to be 1/4 the integral. And now I've got my du, which is just notation at the end. So I've dealt with those. They're outside the integral. That's at the end of the integral. And here I'm just going to distribute so it can be power rule. So here's the key. Here's what really happens on these. Here you can't distribute the x because I have some power here. I've got to resolve that first. My binomial is to the power of 3, or if it was to the power of 10. That's really hard to multiply out. But when you apply this method, it comes down to you've just reversed the two things. The binomial is to the power of 1, and the monomial is to whatever power. And I don't care because now I can distribute it. So u to the third distributed becomes u to the fourth plus u to the third. And now this is a simple power rule problem. So I integrate, and I get 1/4 comes along for the ride, times, power rule says 1/5 u to the fifth plus 1/3 u to the fourth. That should be 1/4, sorry. 1/4 u to the fourth. We'll put in our plus c later. This is not your answer because the question was posed with x's, and you're giving me an answer with u's. You have to then simplify. So we've got 1/20 u to the fifth plus 1/16 u to the fourth. And now how do I get x's back? 1/20 u, that's u to the fifth plus 1/16 u to the fourth. The way we get our x's back is we go back to our substitution here. U was equal to 2x minus 1. So instead of u, I can put back in my 2x minus 1. And if you don't believe me that this worked, take the derivative of this answer, and you will get that original question. All right, so you can't distribute this here because the binomial is to the power of 3. When you do this whole little process, what happens is the binomial should come out to be to the power of 1, which allows you to now distribute, which then allows you to do power rule. Because that's really all we have is power rule, and we know what the integral of some other special functions are, like cosine, sine, e to the x, and ln of x. All right, let's do another one together. How long is this thing? 32 minutes? All right, we're going to get done by 40, or even less, 35. Here's another one. So the other piece of advice I gave you before that I'm going to remind you of here is when our denominator is to the power of 1, then we'll leave it in the denominator because it's going to probably be a natural log. But when our denominator is to like a power, any other power other than 1, we're going to bring it up. So we're going to think of this as 2x plus 1, the quantity, times the quantity x plus 4 to the negative 1/2. So which function would we call our inner function? X plus 4. So we can tell that when we take the derivative of x plus 4, we get 1. That's clearly not 1 here. This has an x in it. So in this case, like, again, I can't do anything with the x part. If it were just a 2, I can deal with constants, but when there's an added x in there, it's tough. You can also see that you've got the powers there that match. That's something else I told you to look out for. The inner function is a power of 1, and then the outer function that you're trying to find, it should be the derivative, so the power should be 1 less, but it's not. It's the same. That's going to tip you off to use substitution. So the inner function here is the x plus 4. Not even looking at the integrand, you just have to. Once you choose your u, you've got to do the derivative of it. It has nothing to do with what's in the integral. I'm just looking here and doing that derivative. So then I separate the variables and solve for dx. So if I multiply both sides by dx, I get du equals dx. So I'm going to use that guy in my integral. And then I want to solve my original u equals x plus 4. I got to find an expression for x. Excuse me. So x equals u minus 4. These three underlined equations I'm going to use to rewrite my integral. So I'm going to recopy it real quick. 2x plus 1 times x plus 4 to the negative 1/2 dx. So I've got the integral of, now I'm going to start making my substitutions. 2, and then x is really equal to u minus 4 plus 1 times x plus 4 is really equal to u to the negative 1/2, and then dx is really equal to du. So what I did was I took out x and I replaced it with u minus 4. I took out x plus 4 and I replaced it with u, and then I took dx and I replaced it with du. So you can see once again that this is a binomial, and I can't distribute because of that power. I can only distribute when that power is 1. Well, now this is a monomial, so I can distribute it over here to my binomial or trinomial, whatever it is, because its power is 1. So that's what's going to happen. First, I'm going to simplify inside here and get 2u. 2 times 4 is negative 8 plus 1, so it's going to be 2u minus 7 times u to the negative 1/2. I don't need parentheses around this part anymore, du. Now I'm going to distribute my u to the negative 1/2 because my binomial is to the power of 1. That's really the magic of what's going on here. It allows you to distribute. So now I've got 2u to the 1/2 minus 7 u to the negative 1/2 when I distribute du. Now I can apply power rule. So I'm going to get the 2 comes along for the ride. U to the 1/2 becomes u to the 3/2, so then it's 2/3 times that. U to the negative 1/2 becomes u to the 1/2. Then minus 7 comes along for the ride. The reciprocal of 1/2 is 2 over 1. So I end up getting 4/3 u to the 3/2 minus 14 u to the 1/2. And I back substitute in whatever my u was equal to, so I have it in terms of x. So in this case, u was equal to x plus 4. Don't forget your plus c. And look at that, piece of cake, upside down.